Hello, I'd like to talk a little bit about conditional expectations. This is for statistics. And let's go ahead and start. And suppose, for example, this is where such a thing might come up. Like suppose you had y is a binomial with parameters n and p, but suppose p, the parameter for using the binomial, is uniform on, let's say, 1/3 to 2/3. In other words, p could be any value between 1/3 and 2/3 with no prejudice toward one particular value or another. Now, normally it would be easy to calculate, if p were fixed, with let's say parameters np, then the expectation for y is going to be np, no problems there. And the variance for y would be np1 minus p, or commonly written as npq commonly. But we have the situation here where p itself is a random variable. So in our case, what we really are looking for is we're looking for the expectation of y given p and the variance of y given p. So that's what we're really looking for, because p itself is a random variable. And you can probably guess how that's going to affect the expectation. You might say, well, take the midway point, and well, that's actually going to give you the expectation of y. The variance, though, you have the normal variance of the binomial distribution. And then you also have the variance that comes with p being itself a random variable. And so we'd like to go ahead and derive the following formulas. So the formulas we want to derive are these. We want to derive the expectation of y, y1, where you have a joint density function y1, y2 in play here. Well, you don't know is the expectation of y1 is the expectation of y1 given y2, where the inner expectation is the conditional one, and the outer one is with respect to y2. So the expectations are with respect to different things. We also want to derive the formula where you end up with the expectation of the conditional variance. So I better rewrite that. Of the conditional variance plus the variance of the conditional expectation. Understanding that this is a random variable and so is this. So the question is how do we derive such formulas? Now, such formulas let's use the formulas before we derive them. So using them, in our case, since p is uniform on 1/3, 2/3, the expectation of p is going to be a half, that's midway, and the variance of p will be 2/3 minus 1/3 squared over 12, which is 1/9 divided by 12, which is 1/108. You'd expect the variance to be somewhat small. So then, in this case, how this works here, the expectation of our original y will be the expectation of y given, in this case, p, which would be the expectation. Well, remember, that's going to be np, and expectation of p, and the expectation of p is 1/2. So this that kind of works sort of in a common sense way. And the variance of y, well, we would have the expectation. Now this, remember, is going to be np1 minus p plus the variance, and this is going to be the expectation of this. So this first one is going to be n times, very good, have it this multiplied here, the expectation of p minus the expectation of p squared, because e is linear, plus, and this is going to be n squared, variance of p, which itself is uniform. So this thing here would be n. The expectation of p is 1/2. Now, this particular thing right here, we do have a formula that, since the variance of some random variable y is the expectation of y squared minus expectation of y quantity squared, this second moment about the mean will be this. Like so. And this is what we have right here. So the variance we already had, this is going to be the variance of p plus the expectation of p quantity squared plus n squared variance of p. And we end up with n 1/2 minus, the sum is 1/108 minus, plus 1. Have to be careful here. 1, the expectation's 1/2, so this is going to be 1/4. Plus n squared, and the x, and we already had the variance of p given as 1/108. And you can work that out. It's not going to, but that's how you calculate the variance. So how do we ever get those formulas to even begin with? That's how you use them. And you can see that the variance of this random variable y has these two factors. It's almost like a product rule situation. But how do we actually derive these? Well, let's look at, and as an aid to deriving them, let's remember what the conditional distribution is. F of y1 given y2 being a constant. Well, what that is you take your joint density function and you divide it by the density function of the second variable, and that's a normalizing constant. And what this tells you is that if you take this and multiply it by f2 y2, you get the joint density function as follows. So now let's go ahead and operate. So if we try to take the expectation of the variable y1, that's integration over the entire range. And keep in mind that what you're integrating, the density function is it has a domain and it has the formula itself. And it has y1, f of y1, y2, dy1, dy2. Now this is where we make the following change. We're going to use this formula that we just derived, to write it like this. We have the y1. Now we're going to write that as the conditional distribution, f of y1 given y2 times f of y2, f2, y2. We'll keep it that way. dy1, dy2. Now, this is where the sleight of hand is. It's not really sleight of hand. This is with respect to y2 as a constant. So you move that outside because you're really like taking a constant outside in essence. And since you're integrating with respect to y1, that's allowable. So this turns out to be, take the f2, y2 outside the first integral. Then I'm going to write this in a different thing here. This is y1. This is a conditional distribution. But then what did you really do? Well, if you write this down like so, this purple thing, this is the expectation of y1 condition on y2. That's what this entire purple thing is. The expectation of y1 with this being your density function. But then you still have the f2, y2. So now this is in fact the expectation of the expectation, as we said it has to be. So that concludes the derivation of this first one here. Now we're going to need a little bit more room. Probably should have planned this a little better. Now let's go ahead and look at the second thing. Let's try to look at the second formula. The second formula, we start with the variance of y1. As we know, that's the expectation of y1 squared minus the expectation of y1 quantity squared. And here the expectation is with respect to the joint density function. But then this is the expectation of the expectation of y1 squared given y2. That's by what we just showed. The inner expectation being the conditional one, the outer one being with respect to y2, the second random variable, minus the expectation of y1 given y2, everything squared. Now this is where we do, and remember I told you this is going to be a little bit like the product rule from calculus. Well, now you're going to see that, because what we're going to do next is we're going to add and subtract something clever. So what I'm going to do is I'm going to switch the color. I'm going to start this as E, the expectation of y1, y1 squared with respect to y2. Now, what I'm going to do is I'm going to subtract the expectation of y1 given y2, everything inside here squared. But because I subtracted that, I had better add the same thing. the expectation of y1 with respect to y2, everything squared. And then I have this black part right here. We haven't changed that. So what I did is I carefully added and subtracted the same thing. Now we're going to use the fact that the outside expectation operator is linear. So given that that's linear, this is equal to the expectation of y1 squared given y2 minus this thing inside here squared. So that accounts for this and this. But then we're going to add to that, do this in black, you're going to add to that the expectation of this thing here, y1 given y2, this thing itself squared, minus the expectation of the expectation squared. Now we're almost ready. Now we see right here, and this is what I want us to note, we have this thing where you have the y1 squared here. Then you have the y1 to the first power, everything squared. Okay, I should probably take that off there, but you can see those two things there. And it's all an expectation. So what's inside here is just the variance. It's a conditional variance. Now added to that, now we have the expectation of this random variable squared minus the expectation of that random variable quantity squared. So that is going to be the variance of, this is a random variable in question right here. Let's put that in maroon. This random variable here. So that's the expectation of squared minus that. So this is now the variance of the the random variable expectation of y1 given y2, which completes the proof. So you just have to be a little bit careful with how you write these things down. So thanks for watching.